kiddos. Welcome back. I think it's time to do a practice problem, sort of bring everything that we've been talking about in this chapter on thermodynamics together. So I've come up with a reaction for you. We have nitrogen gas reacting with hydrogen gas to form ammonia. I've given you some heat of formation values, and I've given you some entropy values for both the product and the reactants. We'll assume that this reaction occurs at 298 Kelvin. So what I'd like you to do, and I want you to do this by yourselves and then I'll do it for you, is part A. So I want you to see if you can figure out a way to find the heat of this reaction, and then I want you to describe that reaction as exothermic or endothermic. So take a minute and think about how to solve that problem. Okay, then come back to the video and we'll see how you did. All right, welcome back. Did you guys think to maybe use Hess's law to find the heat of the reaction? To find the heat of the reaction, can't I take the heat of the products, the heat of formation of the products, minus the heat of formation of the reactants? And when I do that, won't I have the heat of the reaction? Yeah, we've done that before, haven't we? So remember, we take the product's heat of reaction minus the reactant's heat of formation. So what are my products? Well, I've got two ammonias. So I'm going to take 2 times the heat of formation of ammonia, which was given right there, negative 45.9, and that's kilojoules per mole. And that's the only product I have. Now let's subtract out the heat of formation of my reactants. My reactants are nitrogen and hydrogen. So I didn't give those heat of formation values, did I? I didn't need to, that's right, because these are both elements. And what do you know about the heat of formation of elements? That's right, they're 0. So the heat of formation of nitrogen gas is 0 kilojoules per mole. And the heat of 3 hydrogen molecules is also 0 kilojoules per mole. So that makes the math pretty easy. So we have 2 times a negative 45.9, and that's negative 91.8, minus 0 gives me the heat of the reaction as negative 91.8 kilojoules per mole. That wasn't so bad, was it? That was actually kind of easy. We're not done yet with question A. We have to describe it as exothermic or endothermic. And so the sign of the heat of the reaction is negative. That means I'm losing heat, right? Heat is being released to the surroundings. So that would be an example of an exothermic reaction. How did you do on that? Yeah, I'll bet a lot of you didn't know where to start. And then when you watched me do it, you probably smacked your head or shook your head and said, I remember how to do that now. And that's fine. Okay? Well, let's try to do letter B. Take a minute, try to do letter B without my help. I want you to predict the sign of delta S of the reaction, and then I want you to explain how you predicted that sign. And then what I didn't add here is I actually want you to calculate delta S of the reaction. Okay? So take a minute, try to do that, and then come back. We'll see how you did. All right. So let's figure out the sign of the entropy of the reaction. So looks like I'm starting out with 1 gas and 3 more gases. Don't I have 4 gases on the reactant side? True story? And they are turning into 2 gases. So I'm going from lots of disorder, 4 moles of gases, to less disorder, 2 moles of gases. So did you hear that? Less disorder. So the sign of entropy I am going to predict will be negative delta S. Alrighty? Because I'm going from 4 moles of gas to 2 moles of gas. So entropy is decreasing. It's becoming less disordered. I have less gas. All right. Now let's calculate delta S of the reaction. And as you might recall, we can find the entropy of a reaction just like we can find the heat of a reaction. We can take the product's entropy minus the reactant's entropy. So just like we did part A, we're going to do products minus reactants, but instead of using delta H values, we're going to use delta S values. So we have 2 times the entropy of ammonia, which is 193.0 joules per mole Kelvin, minus the entropy of my reactant. So I have N2, and that entropy is 191.5 joules per mole Kelvin, and 3 times the entropy of hydrogen gas, which is 131.0 joules per mole Kelvin. All right, so we'll get our calculators out, and we'll take 2 times 193. We'll get a total on our reactant side. I get positive 386 on this side, minus, we have on the reactant side 191.5 plus, I'll use my parentheses key, 3 times 131.0, and I get 584.5 as the entropy total on my reactant side. So now I can find the entropy change in the reaction. So it's products, 386, minus reactants, 584.5, and I get negative 198.5. And that's in joules per mole Kelvin. How did you do on that? Hey, didn't we say the sign of the entropy change would be negative just a few minutes ago? Didn't we? Said that over here, and we were right. We just calculated its value. All right. Now I want you to try letter C. I want you to find a way to solve for the free energy, or delta G, of the reaction. And then after you've done that, I want you to tell me if the reaction is spontaneous or non-spontaneous. So take a minute, see if you can do it without my help, and come back to the video, and we'll see how you did. All right, welcome back. Did you use the Gibbs free energy equation? Did you use this equation? Delta G of a reaction equals delta H of a reaction minus T delta S of the reaction. Yeah, we've done a bunch of those, haven't we? How come we don't know if the reaction's spontaneous or not just by looking at the delta H and delta S values that we've calculated? Let's see, my delta H is negative 98.1. Nature favors that, doesn't it? Yeah, it's a decrease in enthalpy, right? Heat's being released. However, the sign of my entropy change is negative. It's becoming less disordered or more ordered, which nature doesn't like. So we really do need to use the Gibbs free energy equation to calculate the delta G, or free energy, of this reaction. So let's go ahead and do it. The delta H is negative 91.8 kilojoules per mole. Now some of you are saying, how did Mr. Hummer get that? Well, just remember, folks, let's pick out a different color here. I got that right over here. Remember we calculated that not too long ago, delta H of the reaction? All right, minus T, and if you recall, I said this was at 298 Kelvin, times the entropy change. So the entropy change is negative 0.198 kilojoules per mole K. And do you see where I got that from? Let's take a look right over here. Didn't we calculate the entropy change in joules per mole Kelvin not too long ago? And so I've just converted it to kilojoules per mole Kelvin. So let's plug this in our calculators and see what we get. Negative 91.8 minus, we're going to use our parentheses key, remember, 298 times negative 0.198. Close off our parentheses, and I get a negative 32.8 kilojoules per mole of reaction. So I found the spontaneity, the delta G of our reaction. I need to know if it's spontaneous or not. So the sign is negative. Do you remember? That's right. If delta G is negative, the reaction is Spontaneous, right? I do not have to add heat. Heat is energy is actually being, free energy is actually being released. So that's spontaneous. All right. Now at the bottom here, I thought we'd do something fun. A review from a long time ago. We have nitrogen gas, hydrogen gas, and ammonia. Let's draw the Lewis structures for each of those. And then I want you to predict their shape, their bond angle, and their polarities. So see if you remember how to do that. I know it's been a while, but see if you can shake the dust off and do it. Then come back to the video and we'll see how you did. All right, welcome back. We have N2. Let's do that one first. It has 2 nitrogen atoms. How many valence electrons does each nitrogen have? Let's look at our periodic table. Here's nitrogen. It's in group 15, kiddos. So that's right, it has 5 valence electrons. Whoops. So I'm allowed to use 10 valence electrons here. So we'll put nitrogen next to nitrogen. We'll try one pair between them. Remember how to do these? Then we'll give each nitrogen atom a full octet. Let's see how we did. 2, 4, 6, 8, 10, 12, 14. Too many dots. So let's try a double bond. So now this nitrogen only needs 2 more pairs around it, and so does this one. So how many valence electrons did we use? 2, 4, 6, 8, 10, 12. Nope, we're only allowed 10, kiddos, so that won't work. And so finally, I hope you tried a triple bond and didn't give up. And then this nitrogen only needs 1 more pair. This nitrogen only needs 1 more pair. 2, 4, 6, 8, 10. Yep, that works. So there is our Lewis structure for nitrogen gas. Its shape is linear. There are only 2 atoms in it, so it has to be linear. The bond angle, well, it's just 2 atoms. I guess we could say it's 180. And the polarity would be nonpolar. Right? They're the same atoms and they're sharing those electron pairs exactly evenly. All right, let's try H2 now. So we have 2 hydrogens, and let's see, hydrogen's over here. It's in group 1, so it has 1 valence electron, and there are 2 of them, so I have 2 valence electrons to work with. Well, that's an easy Lewis structure, isn't it? We're done, H2. That also is linear, because there's only 2 atoms, folks, and it is nonpolar because they are the same atoms and they share that pair completely evenly. All right, how about NH3? So we looked up just a minute ago. There's 1 nitrogen, it has 5 valence, and there's 3 hydrogens, they each have 1 valence. So I'm allowed 8 valence. So I'll put nitrogen in the middle, and we'll put a hydrogen on 3 of the sides, and we'll have to put a non-bonding pair above that nitrogen. And I've used my 8 valence. Now, do you remember the shape of this guy? Yeah, it's not a T-shape. I'll bet some of you guys are thinking, that's T-shape, Mr. Hummer. No, remember, this is 3 dimensions. So in reality, we have this pair up here. We have a hydrogen sticking out here, coming out of the paper, and 1 over here, and then this other hydrogen sticking out of the paper. Do you guys remember that shape? Yeah, it's called trigonal pyramid. And that bond angle is not 90 degrees. That bond angle, which would be right there or there, is actually 107 degrees. Pretty close to 107 degrees. We'd start with 109.5 if you remember, because the electron pairs are tetrahedral to each other, but there's that non-bonding pair that takes up more space and reduces the bond angle. And this guy would be polar, right? The dipoles are pulling probably in towards the nitrogen, but they're not symmetrical, so they don't get canceled out. So that molecule would be polar. So I thought that would be fun to end this review. So there you have it. If you could do this problem at the top, you grasped thermodynamics pretty well. If not, why don't you try this video over again? I know that sounds sort of silly. Now that you've gone over it, see if you could do it. All right? Hope you had fun. Talk to you soon. Bye-bye.